All right, so here we are coming back to the spring mass system as it oscillates between your two amplitudes, which I've labeled on the diagram. And it is the maximum displacement from the equilibrium. So we take care of A and B right off the bat. Here, if we start it and stretch it to 1 and release it, it has initially spring potential energy, and that spring potential energy goes to kinetic energy. So our conservation of energy equation would be spring potential energy is equal to kinetic energy, or 1 half Ka squared is equal to 1 half mv squared. Instead of the x, I put in the amplitude because that's where it was stretched to. It was stretched to the amplitude. If we want to know the maximum speed of the cart, which was one of your homework problems, we solve for v. So the halves divide out, and we are left with Ka squared over m equals v squared. You can take the square root, and the maximum speed would be radical Ka squared over m. So the next thing we're going to do here is we're going to actually relate this to angular frequency. So if you look in this term, it has the mass and the spring constant, which are the two things that influence the period. So we're going to relate the speed directly to the angular speed. So we can actually relate the mass and the spring constant to the period itself. So going back to this idea of linear values for motion are equal to angular values times the radius. Well, in this case, the velocity is equal to the angular velocity or the angular frequency times the radius, which, as we talked about prior, in this case would be the amplitude. See the prior video for that discussion. So I can use this term here to make a substitution, which is equal to omega squared times a squared. Well, your a's will divide out, and omega squared is equal to k over m. Omega, if you guys remember, is also equal to, which is the angular frequency, 2 pi over t. So I can also look at this, set this equal to radical km, which would be taking the square root of both sides and then rearranging this whole thing for the period. In this case, this here would address many things. The period is directly related to the square root of the mass and the inverse square root of the spring constant. If you go back to your lab data, both those graphs indicate that type of relationship. This is the actual relationship that exists for the two that impact the period the most. Now, to save you some time and frankly listening to me talk, we will also relate this directly to the pendulum. And the two major impacts on the pendulum were the length, which is if you made it longer, the period increased, and the gravitational field constant. So if you change the planet you're on, if that increased, the period would decrease. So the two equations we're going to be dealing with and that are on your equation sheet are these two right here. One relates the spring mass system, the other relates the length of the pendulum and the gravitational field for small angles. Okay, so these are typically angles under 20 degrees. Now, if you look at that data, the angles, once you pass 20 degrees, that's where you started to see it creep up, the period creep up past the original value. So this equation is good for a pendulum when it makes relatively small angles during its swing.